Hi, this is Ellen Leibowitz, and the problem that I had the most trouble with on Test 3 was Problem 3, Part B. So I'm going to demonstrate how to do this problem for my Test 3 wrapper. In this problem, there was an uncharged capacitor that is connected to a power supply in series with a resistor as shown in the diagram, and current begins to run in the circuit. The square plates of the capacitor have dimensions of 2 meters by 2 meters and are separated by a gap of 0.4 millimeters, filled with air. The resistor has resistance of 350 ohms, length 10 centimeters, and radius of 5 millimeters. The EMF of the power supply is 3200 volts. Specifically for Part B, the question asks me, at the instant before you see the spark, what is the magnitude and direction of the electric field in the resistor? And I also had to show the direction of the electric field on the diagram next to the resistor. So the correct way to approach this problem was to use the loop rule, and you had to use the delta V of the capacitor that you calculated in Part A by being the magnitude of the electric field times the length of the capacitor to get 1200 volts, and you had to use the delta V of the battery, which you were given to be 3200 volts. And using the loop rule, delta V of the battery plus delta V of the capacitor plus delta V of the resistor have to be equal to 0 because delta V round trip must be 0. And then you can rearrange this equation to be delta V of the resistor is equal to negative delta V of the battery minus delta V of the capacitor. And then you could substitute in for delta V of the resistor to be negative electric field of the resistor times the length of the resistor, since these two quantities are equal. And you can divide each side by negative length of the resistor so that you get the electric field of the resistor to be equal to delta V of the battery plus delta V of the capacitor divided by the length of the resistor. And then all you have to do now is substitute in the quantities that you were given inside of the prompt, as well as the delta V of the capacitor you calculate in Part A, and you finally get that the magnitude of the electric field of the resistor is equal to 20,000 newtons per coulomb. And then the direction of the electric field I can show on the diagram. You're shown that the battery has a positive terminal up here and a negative terminal up here, and at the positive end it has a higher potential and the negative end has a lower potential. And you know that the current, or conventional current, is going to be running from the higher to lower potential, so in this direction. So the electric field is going to run in the same direction as the conventional current. So right here at the resistor, the electric field on the resistor is going to be running in this direction.